Last section, we focused on arithmetic sequences, a sequence in which the pattern is that you're adding or subtracting the same value to get from one term to the next. What we're going to look at next are geometric sequences. So our essential question, what is a geometric sequence and how do we write it mathematically? And what you're going to notice is this is going to feel a lot like what we did with arithmetic sequences. We're going to talk about identifying geometric sequences, we're going to talk about recursive rules, and we're going to talk about explicit rules and how to find a specific term. So, what makes a sequence geometric? Let's talk about that first. Arithmetic sequences had a common ratio that we added to get from one term to the next. Geometric sequences have a common ratio, and that means that instead of adding or subtracting a difference to get from one term to the next, we are going to multiply by some common ratio, and that ratio could be a fraction or a whole number. So we are multiplying, I hope it says that right here, multiplying to get from one term to the next. And that gives us our common ratio, and we use the letter R to represent our common ratio. So when we are looking at a sequence to try and decide if it is geometric, we're asking ourselves this question right here: are we multiplying to get from one term to the next? And remember, if the numbers are getting smaller, division is just multiplying by a fraction. So let's go ahead and look at number 1 here first. To get from 4 to 16, we're multiplying by 4. To get from 16 to 64, we're multiplying by 4. So yes, this is geometric. That common ratio, the number we're multiplying by to get from one term to the next, is 4. And then if we find the next three terms, 64 times 4 is 256. 256 times 4 is 1,024. It's okay if you have to do this on scratch paper or on the side of the piece of paper. 1,024 times 4 is 4,096. So looking at number 2, to get from -9 to +3, first of all, I'm going to have to change the sign, which means my ratio here is going to be negative. And what am I doing? I'm dividing by 3, which is the same thing as multiplying by 1/3. So if you ever can't tell the ratio, divide a term by the term before it. A sub n plus 1 divided by a sub n. So in this case, if you're not sure, take 3, divide it by -9. That gives you -1/3. That's the same ratio here and here and here, and you can confirm that by just multiplying each term by -1/3 to get the next. So yes, this is geometric, and that common ratio is -1/3. Why don't you go ahead and pause the video and work on number 3 on your own. Then unpause the video and see how you did. All right, I'm multiplying by -2, I'm multiplying by -2, I'm multiplying by -2. So yes, this is geometric, and that ratio is -2. And I forgot to find the next 3 terms, so I'm going to do that in a different color. Down here, if I multiply -1/9 by -1/3, the next term would be +1/27. If I multiply that by -1/3, the next term would be -1/81. And if I multiply that by -1/3, I would get +1/243. My next 3 terms here, if I multiply 40 by -40 by -2, I get 80 times -2, 160 times -2, 320. So geometric sequences multiply by some ratio to get from one term to next, and that ratio needs to be the same each time. So let's talk about recursive rules. Remember from last class, a recursive rule uses the term before. A recursive rule uses the term before to find the next term. So what we could say with a geometric sequence is to find the next term, you take the term before and you multiply it by r. So here we now have it in math and in English. So here is the rule in that box for our recursive format. Remember that those little values are subscripts. And then when you are doing this, the only thing that you're going to plug in is your R value. So you're going to plug a number in for R just like you did with D in arithmetic sequences. You are not going to simplify. There's no simplification that you could do anyways. So let's go ahead and look at this pattern here. To get from 3 to 6, I'm multiplying by 2. To get from 6 to 12, I'm multiplying by 2. From 12 to 24. So in this example, our common ratio is 2. So our recursive rule, a sub n, is going to equal 2 times a sub n minus 1. And that's the whole rule. There's nothing else to do. So the only number that's going to be changing is that 2, that common ratio. Now, to find the fifth term, a sub 5, we need a sub 5 minus 1. Oops, I guess I should put my ratio first. 2 times a sub 5 minus 1, which means 2 times a sub 4. And what is a sub 4? A sub 4 is 24. So 2 times 24 is going to give me 48. So the fifth term would be 48. So let's go ahead and practice our recursive rule with the three sequences below. Okay, number 4. So a sub n equals the r value, which is 1/5, times a sub n minus 1. That's the recursive rule. This whole thing needs to be here. You need to make sure there's subscripts there, but nothing else should be written. Similarly, on number 5, a sub n equals my r value, 2, times a sub n minus 1, and there's my recursive rule. Go ahead and write the recursive rule for number 6. You're going to have to identify the r value first. Okay, so r is -3, so a sub n equals -3 times a sub n minus 1. Okay, so just like with arithmetic sequences, it's not incredibly helpful to have a recursive rule. I think it's kind of unique and interesting that we can write the rule mathematically out to say, to find the new term, we multiply the old term by this number. But if I ask you to find the 30th or the 50th or the 100th term again, this is going to become really challenging. So there's got to be a better way, and there is a better way, and that better way is using explicit rules, just as we did with arithmetic sequences. So the explicit rule, remember, this does not require you to use the term before. So we're going to talk about how do we write the explicit rule for a geometric sequence. And here is that rule. So a sub n, again, we're going to use the first term, a sub n equals a sub 1, the first term, times that ratio to the power of n minus 1. You are going to often need to use parentheses around that n value, around that r value. And then remember, the order of operation tells us that we have to deal with exponents before we multiply. So what you're going to do is you're going to plug in r and a sub 1 and then do nothing else. Nothing simplifies. Don't multiply. It violates the order of operations. So let's go ahead and do a practice series a practice sequence. Down here, we're going to go ahead and start by identifying what our common ratio is. To get from 3 to 6 to 12 to 24, that ratio is 2. This is the same example that's in that upper box. So we can say that a sub n equals the first term, which is 3, times 2 to the power of n minus 1. And actually, I want that 2 to be green. So if I asked you to find, let's say, the 10th term, we would just plug in n equals 10. So a sub 10 would be 3 times 2 to the 10 minus 1, 3 times 2 to the 9th. And this is a great chance to grab your calculator. 2 to the 9th is 512. And if I multiply 3 times 512, I would get 1,536. So a sub 10 is 1,536. For many of the problems in this section, especially on the homework, please feel free to grab a calculator to do some of this geometric math out. All right, let's go ahead and practice writing the explicit rule for the 3 examples above. So we're going to do this. I'm going to do this in blue. And unlike with arithmetic, there's not simplification. So we're going to start with a sub n equals. We're going to plug in our first term on number 4, that's 500, times our ratio, 1/5, which I'm going to put parentheses around. Oops, that kind of looks like there's an extra number in there. Let's try that again. 500 times 1/5 to the power of n minus 1. Similarly, for number 5, a sub n is going to equal my first term, which is 5, times my ratio 2 to the power of n minus 1. Go ahead and pause the video and work through number 6 on your own. Write that explicit rule out. So I'm going to box my explicit rules. Nothing to simplify, just those rules right there. All right, a sub n equals our first term, which is 2, times our common ratio, which is 3, to the power of n minus 1, and that is my rule. So now we're going to go ahead and plug in the specific term that we're being asked for, and actually I made it a little easier on us. For each of these problems, we're going to find the 7th term. So for number 4, we can say a sub 7 equals 500 times 1/5 to the power of 7 minus 1. So 500 times 1/5 to the power of 6. You can grab your calculator for this. 1/5, which is just 1 divided by 5, to the power of 6 is something really teeny tiny. And when you multiply that number by 500, you get 0.032. 0.032. So we would say a sub 7 equals 0.032. For number 5, a sub 7 is going to equal 5 times 2 to the 7 minus 1, which is 5 times 2 to the 6th. 2 to the 6th is 64, so 5 times 64, which is 320. So a sub 7 would be 320. Go ahead and pause the video and work through number 6 on your own, finding the 7th term. All right, well, this would be 2 times 3 to the 7 minus 1, 2 times 3 to the 6th. 3 to the 6th is 729. And remember, it's okay for you to be using a calculator on this. If I multiply 729 by 2, I will get that a sub 7, the 7th term, is 1,458. So the key things to remember from this section: a geometric sequence is a sequence in which the pattern is that you're multiplying by the same number to get from one term to the next. To write the recursive rule, we have a sub n equals that common ratio, that number we're multiplying to get from one term to the next, times a sub n minus 1. Remember, the only thing you're plugging in there is r. To write the explicit rule, a sub n equals a sub 1, the first term, times r to the power of n minus 1. Make sure you put parentheses around that ratio. And then if you're being asked to find a specific term, you're just plugging that value, the term number in for n, into your explicit rule. So go ahead and write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.